Hello everyone, I'm Sonjoy Dey from Kansas State University. I'm doing my PhD in Department of Mechanical and Nuclear Engineering. My supervisor is Professor Dr. Gurpreet Singh. Today I'll be giving my talk on TMD reinforced polymer-derived ceramic fiber mats. I'll start my talk with the motivating researches that led me to pursue this study. This research paper particularly appeared on Science as early as 2020, which is a highly reputed and respected journal in the scientific community. In this research, a small amount of shear exfoliated graphene was mixed with PAN or DMSO solution to obtain carbon fiber with enhanced mechanical properties. To be specific, a small amount of graphene was able to reduce the porosity or the deformity of the fibers, and the tensile strength was increased to 1916 megapascal, and the Young's modulus to 233 gigapascal, representing 2.5 times enhancement in strength and 1.5 times increase in modulus. In a similar study, multi-walled carbon nanotube was used as a reinforcement agent with polymer-derived ceramic precursor, specifically CERCET, to yield a composite material upon pressure-assisted pyrolysis technique. A small amount of MWCMT actually improved certain mechanical properties such as Young's modulus, hardness, and damage resistance. Finally, in another study, sheet-like hexagonal boron nitride was chemically integrated with polymer-derived ceramic, specifically silicon carbonitride, via simple pyrolysis route. This study suggested that a moderate amount of nanosheet material showed improvements in electrical conductivity, which is as high as doped silicon, but lower than reduced graphene oxide. Furthermore, an increase in electrochemical performance was also observed. Being motivated from all of these recent research works, I pursued my research previous year on a similar 2D material which has a sheet-like morphology of graphite, but an increased interlayer spacing, specifically transition metal dichalcogenides, or I would say in my case, the material was molybdenum diselenide. So transition metal dichalcogenides are made out of transition metals situated in group 4 to 10 of the periodic table, and the transition metals are sandwiched with layers of chalcogenatoms. They were used as a reinforcement material, and the matrix for the composite material that I used was a polymeric precursor named 4-TTCS. To be specific, it is 1,3,5,7 tetramethyl 1,3,5,7 tetravinyl cyclotetrasiloxane. These materials were mixed with polyvinyl pyrrolidine to obtain a viscous and homogeneous solution for electrospinning to obtain fibermats, which were then cross-linked and pyrolyzed at certain temperature to obtain final product. These materials were then examined via spectroscopic and microscopic techniques, which revealed to us the chemical bonds present or the morphology of the fibermats. Finally, these fibermats were used as a freestanding electrode in a lithium-ion half-cell setup, which showed improvement in stability as well as capacity than other electrodes. This work was published in a high impact factor peer-reviewed journal early this year. However, that research posed me with several questions that remained unanswered, which motivated me to move forward with the current research. Firstly, I was thinking, if fibermat with higher mass loading of the TMD material in the TMD and 4-TTCS solution is possible or not. If possible, then what would be the visual representation of the fibermat? How would the higher mass loading impact the spectroscopic or microscopic signatures? Will the peaks in these in the spectroscopic intensify, or will we see a shift of the peaks? Furthermore, I wanted to know if the resulting reinforcement is specific to the TMD material that I previously used, or the similar results can be obtained, or an improved results can be obtained by using other TMD materials. Again, will there be an intensification of the plateaus be possible from the galvanostatic charge discharge graph? Finally, can there be any improvements made in terms of specific capacity, which would yield a much superior electrode material? Therefore, with all these questions in mind, I approached the research questions with two simple hypotheses. So my first hypothesis was that an increased mass fraction of the TMD nanosheets in the pre-ceramic polymer solution can be realized by selecting other TMDs such as tungsten disulfide that are more readily solution processable and low cost. And again, my second hypothesis is that an increased mass fraction of the TMD nanosheets in the pyrolyzed fiber mat may lead to superior fiber properties. According to these hypotheses, I assigned myself with the following tasks. I increased the mass loading of the TMD material in the TMD and pre-ceramic polymer solution. Then I assessed the spinning feasibility of the solution. Next, I evaluated. Next, I should evaluate the morphological properties, and then the electrochemical properties, and then finally, I would evaluate the mechanical properties. So the 2D material or the reinforcement material that I chose was tungsten disulfide because of solution processability and low cost. Moreover, it has a similar covalent bond with transition metals and chalcogen atoms and a weak van der Waals force in the interlayer. And as a result, a rapid and stable ion transfer is possible. Moreover, it has a high energy density because of its large density itself, which is 7.5 gram per centimeter cube. As the matrix material, same pre-ceramic polymer material, which is 40 TCS, was used in the WS2 and 40 TCS solution. I was able to fabricate, many solutions were made using different proportion of WS2 in WS2 and 40 TCS solution, but I was able to fabricate only Fibermats with only 3 solutions with the highest of 15 weight percent of WS2 in the WS2 and 40 TCS solution compared to 40 TCS. And for the method of fabrication, I used electrospinning, assuming that all of you know how the electrospinning technique works. I am proceeding into the next slide. From the increased mass loading of WS2 in the WS2 and 40 TCS solution, it was apparent that the fiber mat looked darker than before, with a similar weight retention after cross-linking and pyrolysis steps. The visual inspection clearly tells us that the more of the reinforcement material might be present in the final fiber mat form after cross-linking and pyrolysis. The effect of increase of mass loading of the reinforcement material or tungsten disulfide can also be captured by the electrochemical signatures, where you can see the intensified peaks in the differential charge discharge curves and intensified plateaus or increased plateaus in galvanostatic charge discharge plots at different voltages. Specifically, the conversion reaction and the ACI layer formation peak intensified for the higher weight, higher mass ratio, and the peak for the intercalation reaction also intensified, which you can see at the lower voltage of the discharge curve and the higher voltage of the charge curve, respectively. Finally, this composite electrode was tested as lithium-ion battery material, which showed a capacity of 600 milliampere hour per gram, which is more than 1.5 times or than that of the traditional anode material, graphite, that is used in current lithium-ion batteries. So finally, we can say that the reinforcement actually improved electrochemical properties, and the electrochemical signature can capture the result. To conclude, Fibermats with higher mass loading of WS2 in the WS2 40TC solution was electrospun. The visual inspection proved that with the increase in the mass loading of WS2 in WS2 40TC solution, um, actually increased the color, or the as-spun fiber mat became more dark. Electrochemical analysis revealed the widened peaks due to the higher mass loading of WS2 in the WS2 40TC solution. In the future, I would like to conduct spectroscopical analysis of the WS2 SiOC fiber mats. I would also like to do the morphological analysis of the WS2 SiOC fiber mats as well. Finally, I'd like to use the same Fibermat electrodes in sodium-ion batteries and potassium-ion batteries to see if the similar results of intensified peaks can be seen or not. Finally, I would like to assess the mechanical properties as well. So thank you again for being present in this talk. Please send me your questions by email. Thank you.